before I get started, just two points. So the first is that I really wanted to thank the organizers for the invitation, and I cannot say how much I enjoyed this week and all the discussions and the exchange that we're having among faculties, but also with the students. I'm really having a very nice week, so thank you all. The second point before I start this presentation, which is a bit different from the one I gave on Tuesday. This one is not exactly in the heart of my expertise. I'm not an isotope geochemist, which is somehow, the whole presentation could be given just on the perspective of isotopes, the chemistry and their isotopes. So it would be a completely different presentation. That's probably the way it's usually given. But since it's not exactly my expertise, so it will be a bit different. And if I'm not exactly as precise as some of my colleagues could be, so I would like to apologize in advance. Okay, so let's get started. So I think that the question that we're asking about the early Earth environment is, we do have this picture in mind at the beginning of the Earth at some point when the Earth was formed and there was an intense magma ocean. And the question is how and when we transited from this harsh environment to this picture that is supposed to be, it's an artistic view of some of the first habitable world environments on Earth, and to this kind of environment it's just a picture that I've taken from on the Spanish coast, where you have rocks that are altered, you have an ocean, you have clouds in the sky, etc. So the question I will try to answer through my presentation is when and how. So the first, I just wanted, before in case I forget, so this was the very beginning of the Earth, when basically a few million years after the Earth formed, probably less than 100 million, it took less than 100 million years to go from this state to this one. The exact timing could be a little debated if we go into the details of the different environments. Probably the stromatolites weren't there. And then to go from this habitable state and potentially with already inhabited environments and to go to the modern functioning of the Earth, we reached this state, which is kind of a steady state at the surface of the Earth in terms of environment. This probably happened around 2.7 billion years ago. The exact tectonic was established. It was not maybe 100%, but it was getting very close to the modern time. So we're starting here from the beginning of the Earth. There was soon the mound-forming impact, and we've talked about it. I will say a few words about other potential ocean vaporizing events. That's something that's debated. I will go through this time, etc. We'll talk about a number of these events, and I will stop somewhere at the end of the Archean. So there's a real challenge looking at the early environment of the Earth. Here, that's a map. It's a map of the outcrops where there are some crustal fragments outcropping. So you see, it's very slow. So it's very low surface coverage of the Earth. So this map shows in a dark orange the rocks. So this color here. So that's the rocks where you could find outcrops older than 3.6 billion years old. So it gets to so that's older than the Archean, and the lighter one, that's everything that's older than 2.5 billion years old. Okay. So this map will come regularly because I will point to the rocks or to the samples that I will describe. I need to go back before there's something I didn't discuss. So I will talk sometimes about the Hadean. So Hadean is the kingdom of Hades, so a warm, inhospitable environment, a lot of heat, probably large volcanoes, eruption. That's how it was thought. And so there's, in principle and by the definition of this Aeon, there is no rock that has been preserved. That's the definition. Doesn't mean that we don't have any record, because we do have some little time capsules that can go beyond that time, beyond that's 4 billion years old limit. That's minerals. I will talk a lot about them. That's the zircons. The zircons are very refractory minerals. They form under convenient conditions that I will describe, and they really help us to decipher what happened through time when the geologist and the isotope geochemist really managed to read the information that are encapsulated in the zircons. The presentation will not be comprehensive about all what we know about the early Earth environment, and it's changing. The knowledge is evolving quite fast. But I decided to talk about stuff that I found important and about which some of the concepts or the common understanding has changed over I would say, the last decade at least. So there's been this claim for a very long time that the Earth was not habitable because of heavy, what's called the LHB, late heavy bombardment. So after the moon forming impact, so claiming with the idea and because of the record on the moon, the record on the moon surface is here, that there was a large number of impacts that hit the Earth about 3.9 billion years ago, with a period of 20 to 200 million years. This means that if that theory or those observations on the moon can be exported to the Earth would have been quite inhospitable until that period of time. So the current understanding, because of the development of the NIS model, and we've heard about it during earlier this week, so I won't get back to it. So that actually questions a lot this late heavy bombardment. And currently, but that may change in the future, there's no real need to have this late heavy bombardment to explain all the observation on Earth and on the moon. So I'm not an expert, but that's what's currently admitted. Of course, this can be discussed, and maybe if you have another lecture next year or in 2 years about it, so that could change. There's also the question about the magma ocean that formed early on the Earth, that allowed also the crystallization of the core, so the segregation of the Earth's core and later the crystallization of the core. So there is an important aspect. What's the duration of this magma ocean? It's not quite clear, and I've been reading some of the latest literature this week, and sometimes in the literature it's due to some different kinds of observations. So people claim that they found some remnants of late magma ocean indicators pretty not so far, so like 3.6, 3.8 billion years ago. That's debated. I think that the common understanding is that the magma ocean cooled quickly, and I use this to illustrate that. I use this modeling by Julien Monteau and collaborators, showing the lifetime of the magma ocean, so it's in million years, as a function of the viscosity of the magma ocean, which has some uncertainty, and its viscosity depends of the exact composition of the magma ocean, depends on what we know about the evolution of the viscosity of magmas as a function of pressure and not depth. So there is some uncertainty, but the actual result should be sometime somewhere here. So we are on the it's a very short lifetime for this magma ocean. So that's the quick message. Another point is in terms of I've talked about in my first presentation that we absolutely, so the Earth was accreted dry, and we need to have some arrival of volatile elements at the surface of the Earth after the core formation, else most of those volatiles would have gone also in the core. So we need something that happens. There is some really nice work. I think there might be some little changes as a function of with the time, but basically the general message is here from Francis Albarrad. After the sun started and the planets formed, that's identified by a number of isotopic chronometers that I will talk about for some of them. So the uranium lead one with a very long period of time, half time. We have here the giant lunar impact, the moon forming impact. And then pretty soon, less than 100 million years after the formation of the solar system, there was the late Veneer that brought the volatile elements onto the Earth. Here, that's a graph that shows that those very volatile elements, but some less volatile, were brought a little later than the origin of the Earth. You have here some age that are reported as a function of, so that's related to the half time of the decay of the uranium to 38. And to be quick, so what this line shows compared, so that's the Earth line. So compared to one of the oldest meteorites, that is the Canyon Diablo 1. So what you see here from this graph is that the general trend for the mid-volatile elements is actually makes the Earth, the delivery of those volatiles earlier than the major age for all the primitive material that made the Earth. This thing here is 4.56 probably billion years old, and the trend for the moderately volatile element on Earth is on the order of 4.4 billion years old. So that's basically this age that we find here. So that's the example for lead. That's easy to measure thanks to, well, easy. I don't do those measurements, so I can say that it's easy. So the terrestrial lead was largely inherited from the late accretion of some materials that was volatile rich. And the very important point is that necessarily happened after the core was isolated from the other part, so the other parts, the silicate Earth. Else that doesn't work. Most of those elements would just follow with the iron into the core. Okay, and as I discussed on Monday, so this is mandatory to have the plate tectonics. It's been mentioned a couple of times during the presentation. We talked about the role of large tidal amplitude for the emergence of life, or the best conditions potentially for the emergence of life in ponds with not too deep, with a little bit of water coming in but not too much, and some regular evaporation due to some heating, whether that's day-night cycle or whatever makes it dry and induce a dry and wet cycle. One of the parameter or the factor that has been called often for this, that's the existence of larger tidal amplitudes at the beginning of the Earth. So that really changed the early Earth environment. And due to the fact that the moon is progressively moving a part of the Earth, and in the early times of the Earth, so the moon was much closer from the Earth than it is now. So you have here the current situation with the Earth here, the moon here, and how you see the moon, the rotation, so the distance, it's about 60 times the Earth's radius. And this is the view 3.4 billion years ago, so that's at the late of the Hadean. And so the moon was much closer, and because the way you see things from the sun, so the moon actually looked much bigger, and that's why in most of the artistic views that you see on of the early Earth, retranscription of some new scientific results, so they are taken by some artists and then making some nice pictures, and you always see in the background a huge moon, and maybe you noticed in my first slide it was there. So that's due to this effect. The moon was much closer than so it was about 3 times larger in the sky than it is today. So that's how that's how we see it today, and that's how it was before. So you may think that there was some, so that could induce indeed some important tidal effect, and I will come back later about it. The distance between the moon and the Earth has been recorded by many authors, and there's a very nice summary by Lopez de Aracevich and Aracevich about 6 years ago. So they actually document, so I've stopped 3.9 billion years ago. So this graph takes off 3.2 billion years ago with how the Earth-Moon distance changed as a function of time toward present day. So they call here from different Archean and then Proterozoic and then Phanerozoic sedimentary rocks. And so you see that how the Earth-Moon distance evolved as a function of time. So those are two distinct points. So maybe we could have something that's not necessarily that steep with big changes. It may potentially be something smoother, but it's not been necessarily completely. It's not like a linear function. So that's my message here. But there's if that's a topic you're interested in, it's well documented in the literature, and so the moon is moving quickly away. Well, quickly, not so quickly anymore, but been moving quickly away from the Earth. But what's the effect of the tidal effect? So if we want to have the large tidal amplitude, a large tidal amplitude would translate into large tidal heat. Else that doesn't work. Here, this is this publication by Heller and collaborators in 2021 from some models where they performed a model of the Earth surface temperature as a function of time. So present is here, so that's the onset of the Earth. So it's based on so this graph takes into account the solar luminosity as a function of time. We've discussed, I think we've heard that a couple of times since the beginning of the week. So the sun was probably much fainter at the beginning. So that's a model here that shows that as a function of time. So solar luminosity as percent of today as a function of time. So we start, where do we start here? A good question. Oh, time before present. So time before present. So we start, so that's the beginning of the Earth. It goes to today. And so you see that the sun at the beginning was not as tough as it used to be. So they took that into account plus some other parameters here and calculate so the Earth's surface temperature. So they make some assumptions about the composition of the atmosphere, but very minimal one. And model so the Earth's temperature. So you have here the base of the sun insolation. And you have here what would the Fenn-Jackson paradox, and so how much you have to put to reach a temperature of 0 degrees Celsius, at least that you have liquid water at the surface of the Earth. And here, so that's the age of the moon forming impact, and that's the kind of tidal heat that could be obtained when the moon was close enough from the Earth. So you see that it's actually not that much. So in any case, it's going to be enough to solve the Fenn-Jackson paradox. So you need, well, that shows that quite some large amount of greenhouse gas is needed in the atmosphere to achieve some liquid water early at the surface of the Earth. And we'll see that we do have evidence for that later. So this question about the role and the importance of tidal effects at the beginning of the Earth and how important this could be for the emergence of life in those warm little pounds that would undergo a dry and white cycle. I think that's something that we should all consider very seriously and not take it for granted. So now I will go to some of the oldest geological record that we have, and in many of the next slides, I will talk here about a locality here that's called the Jack Hills, and the Jack Hills, that's where we do find the oldest zircons at the surface of the Earth being preserved, and we've learned a lot by analyzing those little minerals, trying to get them to tell us as much as they had in their core. So here you have this picture in a false color of I think the oldest zircon on Earth. So this the size of this mineral is about 200 micron in size. So it's a very small time capsule that we are trying to decipher. So what's important to see, so the zircon is a very refractory mineral. It has also it's almost indestructible. So it will, it will survive. It forms at quite high temperature, and can go into various petrological events, can survive even some magmatism, some metamorphism, can be transported in sediments. So there might be some resets eventually, but it retains a lot of information. Sometimes you see here you have the zircon here, so it's how the age is obtained. It's obtained by uranium lead isotopes geochronology using ion mass spectroscopy. Most of it was performed in most of those early measurements were done with the SIMS in Australia. There's a very large facility also that does those measurements at the University of California, Los Angeles. And now, so there are also some other techniques to do those measurements. What you see here, so that's the oldest age that's been measured. So it's one of the corner of the mineral. But some of the ages are different. So there's no way you can give a single age for a zircon. A zircon has a very, you may think that your history is complex and your life is tough and you have a lot of things going on, even if you're young. So this guy is 4.4 billion years old and has seen hundreds of events that are recorded. And as a function of time, the higher our technical capabilities give us the ability to go with very small resolution. So regarding to a micron or submicron, the more we learn about the detailed history of those zircons. So here there's a core, there's another rim here. You do have quartz inclusions. And that's something, the quartz inclusion, that's something that is very important. The quartz indicates that this zircon, so there are not many different ways to make quartz at the surface of the Earth at this period of time. You need to have some magmatic process that are very close to the one we know right now, at present day. The quartz, the juvenile quartz, they are made into when granites formed. So that happens basically in the tectonic cycle. So you may make some fresh new ones in subduction zones given some recycling in the former crust, etc. But you need to have some magmatism. So, and to make this magmatism, that's the same. So there's a very strong requirement to have magmatism on a planet like this, like the Earth, and this was the case also on Jupiter, and it's been the case also on Mars. You need to have water involved to make the magmatism. Because if you don't have water in the mantle at the surface, you won't get some materials to get back down in the Earth, so kind of subduction zones. At that time, it had nothing to do with subduction zones. Potentially, it was just blobs that were going down. But you needed to bring some water with you, some liquid water, to make those zircons. You need that kind of magmatism. There's no other way to do it. So this was potentially an indication that there was some liquid water already at the surface of the Earth 4.4 billion years ago. The exact age of the zircon, maybe I have it later in the slide, but yes, it's here. So in the very popular figure that you see in many books or on the web, so it has exactly those age. It's a very popular one. John Valley has been kind to propagate this nice picture. The age, but it's a picture that's probably from the mid 2000s. So, and the age of the oldest part of the zircon has been revised, and it's just slightly younger. That's the currently admitted age. I wanted to give you also a bit of information on how we measure the ages. The zircon is very refractory. That's first point. A property of the zircon is that they can incorporate a lot of atoms, and in particular the large ions like uranium and thorium atom in their crystal structure, but they reject lead. So which means that at the beginning when they form, they have a very large pool of uranium and thorium, no lead, and so it's easy after that to measure the uranium over lead ratio and to know what the age of those zircon. So the way it's represented, and you may see a couple of those graphs in the literature. So that's how the age is measured on the zircon. So you have this lead over uranium, so 206 lead over 238 uranium as a function of 235 uranium. And there is on Earth, so there is that's the general trend for the Earth. It's called the Concordia. So that's this general curve. When the isotope geochemists measure those isotopic ratio in the samples, it's tough actually to dissolve zircon, so that's why a lot of it is done using isotopes, but then there are ways to dissolve it. So here, so the age that you measure are represented here by those small ellipses. And you get a first intercept between the range that you're measuring in the samples and what's called the Concordia, so that represents the lead-uranium ratio through time. The intersection here indicates where the zircon closed isotopically. Then you may have some other dates, depending on where you're looking at the samples. And then they will align because it may lose some lead. And then there's a second intercept here, closer from present day. And this lower intercept of the chord is when the zircon, so the most recent time where the zircon have lost lead through time. So that's the origin, and that's the last time it reacted. So we usually, most of the age that I will show, they are located here if they're not measured by another chronological method. There's still a bit of uncertainty, and since we really want to go in details on how the surface of the Earth and the environments evolved very early on, so there's a really huge effort over at least 20 years or more than 20 years to refine these ages. So here that's a paper that uses another datation method, so the lead-lead isotopes. The advantage of this method, I think it requires to dissolve the zircon though. This method is insensitive to the recent loss of uranium and even lead, because it will never change the isotopic ratio of lead. If there's an event or a process on Earth that does change element concentration or element ratios, that it's due to their electronic property, their redox state, their affinity toward other ions or minerals or magmas, whatever, but it does not work on the same element. So the lead-lead ratio do not change as a function of time, so it's independent. So here it's a large compilation. So Francis Albared and Jan Blikkertoft worked a lot on this. So that's a large compilation of zircon that has been measured, which age has been measured through this lead-lead age. And that is compared with the evolution. So that's all the record from 3 billion years old here to present day. And what you see here with the distribution in the abundance of zircon as a function of time, that actually represents the evolution, so the presence of the large orogens at the surface of the Earth, because that's where the zircons are formed during these large magmatic processes. Here, so we go back to the distribution of, I think it's in the Jack Hill's zircon, so very exhaustive investigation of what happened at that time. And they show that it peaks here at 4.01 billion years, and there are a number of things here that are below that are considered as false alarms. So those zircons are really important because they tell us that they formed from a magma that is, and this magma has been produced by hydrosmelting of a mantle or previous rocks. And if that happens, that means that there was already free water at the surface of the Earth, and that these processes that led to the zircon looked somehow, potentially with different rock sources, it looked like a subduction. But that evidences the presence of that's here that's the oldest evidence for plate tectonics on Earth. I want to also take the opportunity of this lecture to give you an ideas about other datation method like the lutetium hafnium, so lutetium decay into hafnium, when we do this that with chronological, so we have to choose the half time of those systems, whether you want to date something that's really long, whether you want to have access to the very short-lived elements to really record in detail what happened at the beginning of the Earth. So that was one of my first slides. You do have also a method like those here with isochrones that are potentially a little better than the higher resolution than or less uncertainty than the uranium-lead method. You have to play also with the kind of rock you're analyzing. So you want to have a rock that may stay in the minerals or in the rocks, some that stay mostly in the magma. So that's all the consideration that have to be taken into account. And then spend years to develop the protocol to be able to do the analysis. So here, for instance, you have, it's again about the Jack Hills zircon. It's a graph that's been published by Vinciane Debaille. So hafnium as a function of lutetium hafnium isotopes. So given the kind of decay here, so these ratios plot as linearly, and the slope here is proportional to this exponential time, the decay constant -1. So it's very easy then to get the age, provided all the other constraint has been taken into account. And it's interesting for the Earth and for the silicate Earth to use this ratio because hafnium and lutetium are lithophile elements. This means that during the Earth formation or any process, they won't tend to go into the core. They will stay in the bulk silicate Earth. Uranium is very incompatible, means that it strongly prefers to stay in the melt. And the other one is what we call a compatible element. So when there is some crystallization, it will prefer to go into the rock or the minerals. Plus at the beginning in the zircon, so there is a very low parent-daughter ratio that essentially also frees the initial hafnium isotopic ratio when it formed. So that also allows to see if there are some trends, if stuff has been reprocessed as a function of time. We have the setting point, the oldest time where anything happened, and this rock was formed for the first time. So we can get the composition of the parent melt at the time when the zircon formed, and that also reduces the reduced assumptions to assess the lutetium hafnium ratio of the protoliths. This has been done also for the zircon Jack Hills, and with this method, so the age that was obtained was slightly older than the previous ones. So again, that if we think in terms of the early Earth environment, means that we already had liquid water at the surface of the Earth at that time. So very, very early after the Earth formed. I told you that there was a way to identify the onset of any process that involved hafnium. So that's here the Earth trend in that graph, so the hafnium ratios as a function of time. So if the first magma formed here, we will have this signature, and then a rock will have to plot here. And each time there is a departure, and we have some spreading, we know that there's another event that happened. You see also here that the range of this ratio is not large. So we go here from a little less than 0.28 and we go to 0.285. So then by conveniency, what's done often is to get this Earth line with a zero slope and then to measure the difference. And what is reported in the next line is not any longer this hafnium ratio, It's called the epsilon ratio. So it's just, so this curve here is brought flat. And then we'll see on the top everything that's related to some magma and the residues of that's in the depleted mantle. So the kind of residues will be a little up here, and everything else will be in the negative range. Before I move on to that, let's stay in the Jack Hills region. So there's been this controversial report of potentially biogenic carbon preserved at 4.1 billion old zircon. This is evidence, so that's a paper by Bell and collaborators in 2015. So here that's the zircon that's viewed, I think it's in electron microscopy. So the size is very small. And in this zircon, you see these very light little blobs. And those light little blobs, when measured with Raman spectroscopy, that probes the molecular vibrations, so recognize here the signature of some carbonaceous matter. This carbonaceous matter has been measured for its isotopic composition to check whether that could actually be some carbon that has a biological origin. So how to distinguish biotic and non-biotic carbon? Or there's also another way to put it, so organic and inorganic carbon, because there's always this debate whether organic is necessarily biotic or not. So I think it's not necessarily, but it's been claimed and it's been interpreted the other way in this paper. When looking at the heavy carbon anomaly compared to the PDB as a function of age for a number of zircons or rocks a little younger. So there is we won't go into the details, but there is a general trend. So life doesn't like at all the heavy carbon. So it strongly prefers the light one, so the 12 carbon, the light isotope. So the organic process also tend to be negative. So the inorganic carbon, like carbonates and other carbon-bearing minerals, inorganic, they will be enriched in the light isotope or less depleted in the heavy one if you want. The organic ones, biological ones, will be enriched into the heavy isotopes. So what we see here, that's reports for some organic matter, some old organic matter. Here, that's the study that's reported here from the Jack Hills zircon. There are some other studies from other locations, mostly in I think it's in Ishua or nearby, that had already reported some depleted carbon that had also been interpreted at that time as biological and potentially biological carbon. But there are also some other processes that can change the isotopic ratio. So here that's been claimed, and it could be that later we find that this is actually our earliest indication of the presence of life on Earth 4.1 billion years ago. But that has to be taken extremely cautiously. So there's no agreement on this at the moment. If you have more questions, we can discuss later, because there are a lot of subtlety in here that we can discuss. Now I will get back to the isotope, the hafnium studies on Jack Hills zircons as well. So now you see, I plot things. So it's been plotted. I haven't plotted anything, but so it's plotted here as a function of the epsilon hafnium. So that's the bulk silicate earth trend line that was formerly the slope. So it's been brought back, and you have here everything that's related to the depleted mantle, some stuff that's left, and some melting things. And those zones here are not allowed. All the zircons analyzed here, 4.4 to 4.5 billion years old. So they plot both in this sector. They plot here as well. In this sector here, that requires that early and likely widespread there was a widespread depletion in hafnium of the upper mantle, which meant that partial melting had already started. And what does partial melting? So that requires water, and that starts to make continents. And here, so when we have data points in that sector here. That requires the development of a lutetium hafnium reservoir that's consistent with the formation of the continental crust probably as early as 4.5 billion years ago. So that's one of the oldest evidence that there was some form of crust at the surface of the Earth that required some ocean. We'll move on to another sector that has some old outcrops. It's located slightly so at the extreme west of the Slave Craton in Canada. So we are moving now from a realm where we didn't have any rock, we only had those minerals, and here that's where you find the oldest rocks at the surface of the Earth. So again, they've been analyzed. I haven't multiplied all the isotopic systems. So the analysis of this crust, so the Acasta gneiss complex that's located here, and some other rocks here in the Slave Craton, so the western part. What they basically show is that, so you see they indicate the presence of melting. We could go into the details in what the different, with the different ages, what that means, etc. But there was already the kind of process that I described that happened. We can go into the details and try to assess what was the exact type of the crust, what was the exact mantle, were there multiple processes. I don't think I will go into those details, but that's something that's doable, so you can dig deeper and deeper if you're interested. So that's what's said here. Now I will move also to some indication given by the rare earth elements. We have the most ancient rock that are here in yellow, the slightly younger one in blue. And what we see with those rocks, you see that they have, so we have the yellow, we have the blue, we have this purple one, and we have this black one here that I will try to describe. So you have the heavy rare earth element, and you have the light ones here. You see that the oldest samples that are in yellow here are consistent with what we know with some type of rocks that's called the tonalites. And that's important. I will describe that a little later. It's the way they form. And that brings me also to describe some of the work to which our colleague Hervé Martin has been a pioneer. And Hervé has been really instrumental in the development of the red since the very beginning, I think. And if you have questions, you can also ask Muriel. But it was a very lovely man. I had him as a teacher, and I really always learned a lot from him. And he was also a very wonderful person. Here we go back. So we have this oldest work. We have what's called with the tonalites, and then we have what happens later as a function of time, and we have this typical Archean continental crust that's called the TTG. I will describe what they are in a few minutes. So it's tonalite, trondhjemite, granulite kind of rocks. Basically, what this graph tells us is that for the oldest rock, they have this kind of flat pattern and some strong europium, negative europium anomalies that are typical of the first Earth. And then after that, when we go to some younger rocks, so the blue one, and they have a flat pattern. When we go to younger one, there is this enrichment here and a lighter so depletion here, and it's compared to the chondrites. And these latest trends are very similar to what we have for the Archean continental crust that is a little better exposed and been analyzed by Hervé Martin, his student, Jean-François Moyen, and others. And that requires some specific kind of melting, requires a hot geothermal gradient, and also requires some water. For this kind of rocks, at first order, there is a present-day analog that's located on the southwest coast of South America, and that implies actually that there is a kind of subduction, and the subduction is hot enough, and there is enough water, and that's actually the crust, the crust of the downgoing slabs that melts. So that's really, and that's the unique place on the Earth right now at present day. So that's something that was a lot more abundant at that time. So it was When we're talking about subduction at that time, so that brings me to mention that it was something a bit different than what we are used to now. If we look also at those zircons, basically from the Adian to 8 Archean, etc., all the rocks that are recorded, you see that there is a reference for the mantle zircon in terms of their signature in the heavy oxygen isotope. All the rocks, they go from, they display oxygen anomalies that are spread between the mantle signature and some, what we call this blue line here, the supracrustal signature. And this supracrustal signature, it requires that there is water at the surface of the Earth. So even if we're going, so this graph is not exactly accurate in terms of the dates, etc., and the samples, but that's to give you an idea. It's a simpler one. So since the very beginning here, we do have ratios that testify for the presence of liquid water. Now I will expand a little more on the TTGs from a location that's in the southwestern side of Greenland. It's called Itsak. It's the TTG. There's a TTG complex. So tonalite, trongenite, granodiorite. You have here a typical example of such a TTG. So the gray here, the gray layer, they are the tonalites. Those are potassium pore intrusive rocks, some kind of granitites, so the tonalites. And the white here, that's some granites. The TTG term was coined by a former colleague of Hervé Martin, Birmingham, that I also had the privilege to have as a teacher at the University of Rennes. And this first term, TTG, that you will see if you're interested in the early Earth in different publications that appeared in the literature in 1981. So you see here from that rock, so again, all the way, so a couple of zircons here that are described, and the holes that were made by seams to do to put some ages on those processes. It was to show you how those rock actually look like. So the TTGs are known to be substantially, they have this characteristic in terms of how they're looking. They contain a lot of old zircons, of course. And practically we consider them as the result of the melting of hydrated mafic crust in a zone where there is a garnet left into what's left after the melting. So not too deep. So they are known also to be substantially enriched in very incompatible elements. That's a characteristic that's inherited from the extreme differentiation of the magma ocean in the presence of garnet. So you have here, so that's for the, I think I said mistake, so that's the light rare elements here, and that's the heavy one, so we're going to have to correct that. So that's a typical trend in rare earth elements for the TTGs with high, so very steep slope with high light rare earth elements and low heavy rare earth elements. They don't necessarily show an anomaly in europium, and they have a very low, so the europium is here, so there's no anomaly. The anomaly here is in titanium. They are depleted in titanium, and this low titanium content, when we do the analysis, so some petrological experiments, that's actually characteristic of a low temperature melting, and the low temperature melting that's represented here for some of the experiments, it's characteristic of a hydrated system in the presence of amphibole. So you cannot, you have here this graph that represents some, so pressure as a function of temperature, the courtesy for Hervé Martin, when he received his prize. So you have the current mid-geotherm, so evolution of temperature with depth. You have the Archean geotherm that was hotter, because the Earth was hotter at the beginning due to the initial accretion and the decay of the short-lived elements. You have a number of graphs here. You have those two green lines that are important. This zone is the breakdown of the hydrous minerals. You have two yellow lines that are, you see, a very different shape. That's how the mantle would melt in case it didn't, or the rocks would melt in case they didn't have any water. It's the shape that they would have if they have water. So you see that when there is water and the geotherm is high, so it's very easy to enter the melting zone in this kind of region, so kind of low temperature, below 800 degrees C, and very low in depth, a couple tens of kilometers. That's the model for the formation of the TTGs, and this model is due to Hervé Martin. So that's so also in terms of mineralogical composition, I said that those rocks, they had this characteristic of being poor in potassium. So you see here you have the feldspar, so anorthitic, so that's rich in calcium and aluminum. So you have the orthos here that's rich in potassium, and this one is rich in sodium. So you see that all the TTGs, whether that's tonalite, trondhjemite, or granitoids, they plot on this plot, so they are depleted in potassium. And they are signature of that kind of process that only happens if there is the hydrous melting of the rocks. That's how. So thanks to all these information, so that's how the schematic model for the formation of the continental crust. And so the first one was probably made from some hydrous metals and made some TTG plutons. And then after that, so there was a further remelting and differentiation. So, and we can put some ages at different times. So the first one that described in this paper, it starts here, but we'll see that it's probably started a lot earlier, and then 3.6, and then we move on as a function of time. And as a function of time, we can remelt the most evoluted rocks, and we can make even more evoluted ones, richer in silica and more depleted in some elements that have characteristic. So that's the kind of rocks and how that work. Let's try to go back now to some larger numbers. So how the continental crust grew as a function of time. There's no 100% consensus on that. So earlier model had a very slow growth as a function of time. So it's normalized here to the current continental mass here, and that's as a function of time. We're here at the beginning of the Earth. And then most of the models now, they go to a very sharp increase of the continental crust very early on. Most of the reasonable models are in this brown shape, and they are consistent also with some actually original data from Armstrong in 1981. So it means that the continental growth, so it started very early and then built up actually very quickly, and the total amount of the crust, the continental crust that we do have at present day, was already there in the Eoarchean. So after that, it's been reprocessed. We can move on now to another location. So we are going to move. So we're traveling a bit here. So we are going now to Greenland, and we are going to some of the oldest rocks also on Earth that are located in Ishua. We're in Ishua, so I've talked a lot about granitoids and TTGs, etc. Here in Greenland, so we have some beautiful outcrops of a former ophiolitic sequence. So here that's a serpentine outcrop that's been taken by a dear collaborator of Francis Albaret Minicrosing. The samples are taken from this region here, where you do see a lot of these green colors that are typically so related to rocks that we would find currently in typical subduction zones. So they've been investigated, and in particular by Marie-Laure Pons. She's measured the zinc isotopes of these rocks. What's important here? So on the top here, you do have a number of old rocks. I think that here you do have the Ishua serpentinites that have this signature here. You do have, for comparison, some serpentinites from the deepest trench, subduction trench in the world, and the Mariana Trench of Japan coast. Then you do have the signature of a mid-oceanic ridge, of ophiolite, of some marine shells, of something else here that you can potentially read, some pebble nodules, and here the deep sea carbonates. What's really interesting is to see that these Ishua serpentinites, their signature is very closely related to the Mariana serpentinites, and there's no really other way to interpret it. The zinc isotope under those conditions and plus modeling, they show that they are actually a very good pH meter. So this signature here on this side is typical of very alkaline water. And if I wanted to give you a view of the environment that this issue assigned, like in the Mariana right now, it's typical of what we call the mold volcanoes serpentines. I've talked about it in my first slide, where some forms of life, deepest forms of life, could be present. Here, that's a picture of an active mud volcano at the bottom of the Mariana Trench, and that's a fossil one that's been sampled and observed and sampled by an IODP expedition a couple of years ago. So that's really characteristic with high pH, hydrothermal conditions, medium temperature, 100 to 300 degrees C. And those conditions, so that's high pH, it's also very conducive, reducing conditions. So that's also conditions that are very interesting so we've talked yesterday about the chemistry that is needed for abiotic reactions and potentially reactions that may form life. Under those conditions, they are optimal to make amino acids, for instance. Abiotic amino acid that works very well in those conditions. So that's in this former, so in Ishua. So Ishua is about 3.8 billion years old. So there was something that was very closely related to the Mariana system. In the Ishua rocks, there's been also potentially some biogenic carbon identified, 3.7 billion years old. So from the isotopic signature, so the light carbon signature, but also like the former samples, so trying to go into the samples, look for inclusions, do some infrared spectroscopy here with some different resolutions. And they didn't observe neither CH nor OH, but they've observed lots of those bonds that we've learned yesterday that are important in the abiotic, in all the first elements that could later form life. But again here, what's important to see is that it's been transformed by metamorphism, and now it's been more or less graphitized. So we still have some information on the bondings that were present in the organic matter, but whether we can claim that it's life or not, it's a big step. That if you want to publish a high profile, if you want to have a high profile publication, a lot of people are actually tempted to do it. So that's also one message for you. But there's a number of evidence, but there's no final answer right now, to be honest. Maybe, maybe not. But that could be. So maybe if we discover some new way of analyzing these samples, we may be on our way. So we do have crust. We know where it formed. We do have a lot of water at the surface of the Earth. We want to know when we had some continents emerge, some landmass at the surface of the Earth, and when was this subduction happened actually. Here, that's a paper that's been recently published, and that's very convenient. So it analyzes the barium concentration in some rocks of the oldest craton that actually have the property to track the onset of subduction zones. So the richness in barium is typical of TTGs, and it can be produced only in lower geothermal gradients with corresponding to some hot subduction zones, and that can be reasonably used as a proxy for the onset of subduction zones. So the example that I gave you previously has been sampled in the different cratons. So you see they are all here, and what you see is that the beginning of the subduction zone that is marked here by this little step occurs in different location in these different cratons. It transforms into global step changes, where you can say that potentially, so the subduction started at the surface of the Earth massively, I would say, because it started earlier in some locations. So massively, it started around 3.4 billion years ago, or a little later, and it was well established after 2.7 billion years ago. So that's really the time where one can say that potentially something that's getting very close to the modern plate tectonics started. So there was this transition between 4 and 2.7 billion years ago. So this modern tectonic gave some subaerial land masses that we like very much in terms of locations where we could have the emergence of the origin of life. So that's been done using a large data set of measurement of the potassium of a lanthanum ratio. Lanthanum cannot be removed by erosion or interaction with superficial water, whereas that's the case of potassium. Potassium will just leave the rock, is water soluble, and will just leave the rock during weathering and alteration. What we see here from that record, so as a function of time, present day, AD and Archean limit, so you see that at the beginning, so there was little weathering until 3 billion years old, and then weathering started very intensively between 3 and 2.7 billion years ago, and then started more or less like it is now. That's also consistent with the signature in the strontium isotopic ratio of the sedimentary record that gives us access to the weathering in seawater. So here you have, in terms of strontium ratio as a function of time, so here that's the ADN Archean limit, and we go toward modern time. So that's the mental contribution. It's the signature of a number of rocks, and you see that all the ratios after 2.7 billion years old are pretty high. They really go further. That's the seawater evolution that makes the minimum. So we had at that time really in interaction, we had the signal into the seawater of this weathering. So that's absolutely consistent, and so meaning that before 3.3 billion years old, there was virtually no land masses, or very little, and then after that, within 300 million of years, we went to the modern regime in terms of weathering and alteration. And in terms of timing, you see that predates the Great Oxygen event that I won't necessarily talk about in this presentation. So now we are going in the Pilbara region. So Jack Hills were here, Pilbara is a little north. This is a very recent paper that is very interesting. So Brenner and collaborators in 2020 managed to, in volcanic samples and basaltic samples, more precisely, of the former basaltic samples from the Pilbara cratons, so they've been metamorphosed, but they were able, so the magnetic field had already started on Earth, that's also a proof, but it started earlier than that. So they were actually able to retrieve the magnetic pole of those samples. Those samples were about 2.2 billion years old. And so they were able actually to see how they moved through time in terms of latitude, because the paleomagnetism, the intensity orientation, allows you to see how the continents moves, not in terms of longitude, but in terms of latitudes only. And what you can see here, so that's the evolution in these rocks, Pilbara and Cape Val, that's in South Africa. So the paleolatitude as a function of time for those samples. So what's really interesting is that starting around 3.3 billion years old, so you see that before that, that was a very mild velocity for plates, if there were plates there. But then from there on, you see that plates are moving with this kind of, so that's how they moved. And when we translate that in terms of plate velocities, so that translates into something for this zone here, that translates into something that's 2.5 plus minus 1 centimeter per year. And that's something that's very similar to the velocity of plates in the modern plate tectonics. So that's also another way, another element that works well in terms of the onset of the modern plate tectonics at that time. So here that's also another way to describe the time average per year in different locations, in different rocks. And I won't comment this one. We had modern plate tectonics. We have also, in another context, so we're getting, this is a worldwide analysis of the bending the bended iron formation. Here that's from South Africa, Barberton. This picture is a beef from 3.2 billion years old. And again, Pons and collaborators. So Marie-Laure gathered a lot of bended iron formation from all around the world. She did the zinc isotope analysis through time. So here we're at the Archean limit, and we're going to modern time. And what you can see here is that as a function of time, there's been a very important change in terms of the isotopic ratio, the heavy zinc signature. So we go to less heavy and then heavier again towards a modern situation. So you see that in this range here, between 3 and so that ends at 2.7, and there's this big change here, and then go to 2.4, 2.7, 2.5 billion years old. There's been a huge change, and that changes here, that goes toward modern time, is consistent actually with changes in pH and other stuff. And the short message is that the signal shifts significantly between the time that I've just highlighted, and that's typical of the dissolution of the heavy zinc isotopes. And so that means that before 3 billion years old, we didn't have any exposed land. That started barely between 2.9 and 2.7 billion years. It became more important between 2.5 and 2.3, and then we reached the modern time very quickly. So there was already a lot of stuff there. The mass of the ocean, it's from serpentine in the Ishua supracrustal belt that I've already presented. So thanks to the isotopes, oxygen, hydrogen isotopes, Poppy and collaborators ended up with this kind of location for the Archean ocean 3.9 billion years ago. So we had an ocean that was between 1.5 and 1.8 times. It was, let's say, 100% the mass, 110% the mass of the present-day ocean. So well-developed ocean, a little more than we have before. This is also confirmed by a number of publications. So in terms of we have indications of the pH of the ocean that was slightly acidic. Right now, the mean pH is about 8 for the ocean. It was not so rich in sulfate. It barely contained oxidized nitrogen species, a bit of ammonia. It was, of course, because of the beef, it was rich in ferrous iron. The salinity here is written, so can go to 20 to 50 grams of salt per kilogram of water. So there's a debate whether it was a little more salty than present day. But the chlorinity was different from what we have before. It was probably more salty than it is at present day. So that's documented in a number of samples all around the world. The long term of the cooling of the ocean, that's a debated topic. Here, that's a paper by Garcia. So where we have here represented as a function of time 3 kinds of information: the oxygen isotopes, the silicon isotopes, and also a biochemistry study that analyzed the nucleoside diphosphate kinase from a number of samples from light requiring prokaryotic and eukaryotic phototrophs that are very widely spread in terms of their divergence age. So go back to the Tree of Life lecture that we had yesterday. The authors here claim that so around 3 billion years old, so the ocean, the surface of the ocean was quite hot, maybe up to 75 degrees C, and then cooled down slowly until 1 billion years ago, and then it stayed like this. Well, we're actually more in this range here, so there's a little inconsistency to start with here. And from some other isotopic ratios, so potentially it was hot during the Archean, and then it cooled more rapidly, you see, as a function of time. But I will show in some next slides some other modeling that really integrate a wider range of information. They actually tend to prove that the Archean ocean was not so hot. That's how the early Archean looked like. It was green because of the ferrous iron in richness in the ocean. And you had a little bit of continents as compared to the early Earth. This graph here, I could change it here because everything, as you see, changed importantly between 3 and 2.7 billion years ago. For the atmosphere now, I think you do. For the atmosphere, we have a lot of information. I don't want you to read this table, okay? To be clear, it's just to show that there are a lot of bases for the different constraints that have been taken into the models, whether that's some former independent modeling, whether that's data in the samples, whether that's chemical measurements, whether that's isotopic measurements. So it's a really wide range of information that are integrated when we go to these kind of curves. So here, that's a representation of the atmospheric carbon dioxide as a function of time. So you have the Phanerozoic time and how that decreased as a function of time. So that was quite high at the beginning, and that's necessary actually to reconcile with the Fenton sun paradox. The atmospheric methane, this kind of curve, it has some constraints elsewhere. So that's how it looked like as a function of time. So it was pretty high, decreased steeply, and then moderately, and then there was this, of course, huge drop when there was the great oxygenation event. Another important gas in the atmosphere. So barely at the beginning of the Earth, but I think that there was virtually no oxygen. The partial pressure of nitrogen, however, can span quite a large scale. So that's how the evolution, the nice graph that you see usually as a function of time. You have here the temperature of the atmosphere through time, and the partial pressure that goes to the present day atmosphere here with mostly nitrogen. So you can really see how these things evolve through time for the nitrogen that increased a little bit, for the carbon dioxide that decreased as a function of time. You have here the oxygen, of course, that rose about 2.5 billion years ago. That part here, I should emphasize that it's somehow debated. How overpressure that was, there is some debate here. And then you have the concentration in methane. So that brings me to some graphs or some schematics that were proposed by Nick Hunt and Nisbet in 2012, comparing the Hadean Earth and the early Archean photosynthetic world. We have refined a number of those detailed in the environment, but basically that has not changed so much. We could discuss exactly the gas in the exact gas in the atmosphere, the temperature of the ocean, but that's basically how it was. And I was talking about, so now about the early Earth environment in terms of the ocean and the atmosphere. That's a very interesting work that's done by Charney and collaborators. So they run a global climate model trying to integrate all the information that they had. And so, of course, it has some large error bars that are in gray here, but the main tendency are in black. So for the pH of the ocean, that was more acidic as a function when we get back in time. The atmospheric CO2, that is not so poorly constrained here. Less constrained, that's the outgassing of the Earth. The temperature of the surface of the Earth, and you see that here at the beginning, so here we do have some strong inconsistency with the other information that we have from other proxies. So that's an issue here. So that's something that has to be worked out. The continental weathering, we talked about it, the seafloor weathering. And so that's in this context, actually, that life emerged with potentially some forms of potentially here. Emmanuel Javot was even more optimistic than I am, more than 4.3 billion years ago in her presentation. But the oldest well-established traces of life in that context, from what we know, that's in the Dresser Formation in South Africa, and it's around 4.5 billion years old. And with that, I will stop here.